Good morning, good afternoon, all over the world. Today, I'm going to talk about human systems integration. And more specifically, I like to address the flexibility challenge. The purpose of this talk is to see how technology, organization, and people could be orchestrated from the very beginning of the design to the end of the life cycle of a system. And I'll talk about socio-technical systems. I like to include in systems the people. The idea is, when you look at the COVID these days, we had to solve problems dealing with the unexpected. And then we need flexibility. We need to anticipate, prepare, be creative, and use a lot of experience, sometimes contradictory. The idea is to shift from rigid automation. This is what we have done for a long time. We automated people with procedures and machines with automated. Today, we are talking about autonomy. It's very fashionable, autonomous cars, for instance, even if sometimes we think that we should talk more about semi-autonomous, but the key concept is flexibility. How can we make a technology that enables us to be more flexible and not constraints when things are going wrong? I like to talk about human-centered design. You know that I've been working in human-centered design for a long time, but human-centered design of social technical systems, where these systems are complex and life critical. I like to talk about well-being, safety, sustainability, and efficiency. And more than anything else, I like to put the artificial at the service of the natural and not the other way around. My world for the last 40 years plus, in fact, and probably more, 45 years if I include my PhD, I worked in aviation and space. In aeronautics, I worked on cockpit design for a long time, worked on most cockpits of Airbus, and I worked in space. I worked on the shuttle. I worked on the Lunar Electric Rover, SCV it's called now, a space exploration vehicle. And I worked on mission control rooms, firing rooms. What I learned is that we shifted in about 45 years, last 45 years, from corrective ergonomics to interaction design, and today to human systems integration. And other things, of course. Human-centered design. I wrote that in a book in 2013. It's called Orchestrating Human-Centered Design. But HCD for whom? In my field, of course, it's for pilots, controllers, maintenance personnel, airlines, etc. But it's also for engineering designers, for developers, for manufacturers, for certifiers. In fact, HCD is for everybody at work, and not necessarily at work, in our lives. HCD assumes that there is always the human element everywhere. But how do we consider the human element? What are the theoretical and practical methods and tools? Okay, we'll try to answer this question during this keynote. HCD of socio-technical systems should be investigated today in a digital world. We need to co-design technology, organization, and people's activities. We don't design people, but we design their activities and their role and things like this. So we need to think about the life cycle of systems. It's not only at design time, it's during the whole life cycle of a system. This diagram was put together by a team of research scientists, engineers, practitioners who belong to the Human Systems Integration Working Group of INCOSY. We have three major disciplines: systems engineering as a source for human systems integration, with the socio-technical systems, system of systems, agile development, design and system thinking, model-based system engineering. And we have also human factors and ergonomics. I mean, this is the topic of this conference, where I try to put a few lines here. Of course, it's not exhaustive, but I put task and activity analysis, human and organizational performance evaluation and metrics. A third source of knowledge is information technology or computer science, with human-computer interaction, artificial intelligence, visualization techniques, and most importantly, I think, modeling and simulation. But these three sources of knowledge should be completed by the operational domain where you work. So for instance, if you work in aeronautics, then you need to know about aeronautics. And if you don't know yourself, you need to have somebody in the team that is an expert. This is why, you know, we need to foster operational expertise and knowledge and experience. This is for scenario elicitation. Scenario-based design is really a very important topic. And experimental test personnel. Now, if I want to focus on human systems integration, here we elicited 11 perspectives that include safety, competencies and professionalism, sustainability, habitability, occupational health, social, cultural, and organizational factors, training, HSI planning, human factors engineering, workforce planning, integrated logistics support and maintenance. Of course, this is not necessarily exhaustive, but that gives you an insight of what we are doing. Now, if I go more in the center of human systems integration, and I already talked about that, there's this triptych: technology, organization, and people, the top model, within an environment. And of course, human system integration at the center. Now, I talked about automation and autonomy. Let me show you the emergence of contributing disciplines, probably engineering disciplines here. Rasmussen's model tried to capture the human behavior at three levels. The skill-based behavior, this is the subconscious level, a stimulus response, if you want, from sensor to effectors. Riding a bicycle, for instance, is this level. This level was put into the machine a long time ago. The first autopilots were developed and used in the 1930s on commercial airplanes. And we never stopped to refine these developing control theories, especially in the 1940s. Norbert Wiener developed the cybernetics here, and electrical engineering, mechanical engineering control theories further developed during all these years. The second level of behavior is the rule-based behavior, as Rasmussen put it, where, you know, this level is conscious. You have to think. You need to recognize a situation using a situational pattern that you learned before, and this situational pattern is usually associated with something to be done, a task or procedure. This level was transferred to the machine in, let's say, the 1980s. A good example is the flight management system, the FMS, that is on top of the autopilot, and this is for navigation purposes. The autopilot is for flying purposes, handling qualities, and the FMS is for navigational things. The disciplines that were developed and used were and still are operations research, optimization, expert systems at the time. Now, if you don't recognize the situation, then you need to do something, and you go to the knowledge-based behavior, where you need to make sense of the situation. You don't know what it is exactly, but you need to make sense. You need to identify this situation. And then you need to make a decision with respect to goals that you have. And then you need to make a plan. You need to make procedures. You need, instead of, having the procedure ready to be used, like in the rule-based behavior layer, then you need to make the procedures there. And here we developed a discipline called cognitive engineering. It started with Don Norman in the beginning of the 80s, but human and social sciences were really at the heart of this level for a long time. We went from basic automation to supervisory control and to human-machine teaming today. This is where the autonomy is located. Some people think that with machine learning stuff, with artificial intelligence, we could actually make machines that handle this level. At the moment, really, people are the only agent capable of handling this level. So we need to deal with complexity. Imagine that we want to go to Mars, or we want to go to the moon first. I mean, we did that before, in the late 60s, beginning of the 70s. 12 people went to the moon and worked on the moon. So you need to have an approach that tries to better understand the complexity. It's not a matter of simplifying things, it's a matter of being familiar with the complexity. And then you need to design, a ground-based control room, for example, a spacecraft. And then you need to identify the various functions that will be useful. And then you need to simulate that. And then you need to experience that. And you need to do it. That's so in fact, dealing with complexity is a matter of becoming familiar with this complexity. It's a matter of being exhaustive enough in the description of the various structures and functions. And it's a matter of dealing with the dynamics of the interactions among these functions and structures. So I like to show you that the complex system should be considered as a living organism. Medical doctors and physiologists and biologists know for a long time the separability property of a complex system, biological system. That means that you can separate apart an organ, for instance, from the body and put it back and it works, But some organs like the brain, I mean, you cannot separate that. Otherwise, you kill the overall thing, the system of systems, if you will. So that's the first thing. So in fact, you need to understand what is separable and what is not separable. The second is to understand that the complexity is not only in the nodes, in the functions and structures, but also and most importantly, in the links, the connections between these. And then when you put this at work, you have these yellow functions and structures here that we call emergent functions. And the more you know about these emergent functions that are not really available in the beginning, before you put that into operations, then the more you know, the more you master the system, and the more the system becomes mature, if you want. So to summarize and put that together, the properties of a complex systems is the large number of components and interconnection among them. Think about the brain, for instance. Millions of billions of interconnections, you know. Many people involved in its life cycle, you know, I'm talking about the complex systems, engineering systems, you know. They are disseminated all over the places, but they also in time, you know, from design to development, to manufacturing, to operations, maintenance, and dismantling. The third point is emergent properties are important in behavior. And they are not included in the components. They come up during the performance. Also, we need to deal with adaptability. You know, there are mechanisms that are adaptive and produce this adaptive behavior. So we need to better understand this. Also, the unpredictability, this is due to the nonlinearities of the system. For a long time, we tried to linearize systems in order to simplify them. As I said before, simplification is a thing, and that's worked. It worked pretty well during the 20th century. But we tend to remove the nonlinearities because we don't understand them too much, and we try to stay within the context of the linearities. But sometimes we get out from this linear context. And then what do? Example, COVID. So let's talk about integration. And integration is done most of the time too late. So let's consider integration from the very beginning of design. In order to show you how we could do that, the traditional approach of engineering, systems engineering, going from design to dismantling, the axis here. And then you have three curves here that are important. The first one, the red one, is the resource commitment. We commit to the resources too early most of the time. The manufacturing companies, I mean, deal with suppliers, and they need to make business and things, and they commit very early. That follows that design flexibility drops drastically as you commit with the resources. And also the green curve is important. You know, you learn about the system as you develop it and as you use it, most importantly. So what we would like is to shift this green curve to the left. So if you use modeling and simulation, and most importantly, human in the loop simulation, very early, at the very early stage, and this is possible today. We have these virtual prototyping tools that are really ready to be used and applied to what we're talking about. So in this case, I mean, you can learn about the system much earlier than before. With a little reservation here, that is actually the system here is most of the time virtual. And then the issue of tangibility is a real one. So we will come back on this because Industry 4.0 deals with this kind of thing. And design flexibility can be kept at a very high level for quite a while. So in fact, you invert the concavity of the curve, going from the design flexibility curve on the left to the design flexibility curve on the right. And then at the same time, the resource commitment follows exactly the same symmetry from the left to the right diagram. Some people tell me, you should put the red curve a little bit higher because you need to invest in modeling and simulation tools. So you're gonna spend some more money there. But still, in the end, you're gonna have more or less to redesign or redo because you anticipated a lot of things at design time. As I said, this approach is true during the whole life cycle of a system. And this is a project that we have right now in my lab together with a company making engines, where we develop a digital twin of an helicopter engine for maintenance purposes. And in order to better understand, what is going on when an engine fails, and you have to provide advices remotely, and then you can place some what ifs as you wish. So in fact, coming back to this diagram, if we expand the modeling and simulation to the whole life cycle like this, and I call that digital twin because the modeling and simulation is about the system that you are designing and using, operating, and probably one of these days dismantling. So I expand the human in the loop simulation to a digital twin during the whole life cycle. And I can play what ifs. I can consider as well that this digital twin is a vivid documentation that I maintain during the whole life cycle. I can integrate experience feedback in it. And this is a kind of organizational memory. Digital twins can be considered as virtual assistants. And here we enter into this field of multi-agent collaboration with people, but also with these digital twins. And these digital twins could be considered as mediators for collaborative work. This is what we're doing in my lab right now. Let's talk about automation and autonomy again. I already said that you can automate people by providing them with procedures that they need to use, and then you automate the human functions. Same thing for machines. We call that automation, of course, for machines. And you automate system functions. But all this is valid within a very well-defined context, or well-defined context plural. And it becomes very rigid when you get out from this context. It's rigid actually anytime, because you push the button and either you use a procedure that is pre-established, or you start the automation and then you monitor the automation. So this is for expected situation. What do we do for unexpected situation? Then you have to solve problems. And problem solving is totally different from procedure following and automation monitoring. People are the main actors there. And most of the time you have several people, several agents, several actors, and that need to be coordinated. The more you have autonomous agents, the more you need coordination roles. But all this is within a flexible framework. And this is where I like to put my keynote. All this could be understood as a schema for function allocation, human and machine function allocation. On the rigid side for automation, and on the flexible side for problem solving. What kind of technology, organization, and competencies we need to be flexible when you need to be. This is what the FlexTech chair enters to play. This is I'm actually the director of this FlexTech chair. So from rigid automation to flexible autonomy. Sorry. Another way to handle this is, and to understand it, is to see the evolution of human factors and ergonomics. Human factors and ergonomics was born after World War II. And in fact, the people were there, mainly physicians and later psychologists, to provide some remedies, corrective ergonomics to engineering products. And then they observed activity before the design and after the system was developed, but not necessarily during the design. That was difficult because that was impossible to do significant things, because you could test only parts of the complex system. And you needed to wait the end of the development to test the real thing. Then came human-computer interaction in the mid-80s. That came with the microcomputers that spread around the world. And here was born interaction design, human-computer interaction design, and lots of task analysis methods and tools. Since the beginning of the 21st century, complexity came to the point that human systems integration within system engineering, in fact, started to be developed. But the good news here is that we have modeling and simulation tools that we didn't have before. I think for the last 20 years, we can test activity at design time. I just remind you the distinction between task and activity. The task is what is prescribed, and the activity is what is effectively done. But all this, as I said before, can be done in a virtual world. Then we need to emphasize the tangibility issue. Another way to see that from an engineering perspective is to say that before the 1980s, hardware was dominant. And all the human factors and ergonomics was really related to physical issues and physiological issues, like biomechanics and physiology in general. Between the 1980s and the 2000, human-computer interaction was born, and of course, this is also what I call artificial intelligence 1, as a distinction with artificial intelligence 2 that we know today. And cognitive engineering developed a lot, computer graphics and software engineering. Today, HSI is really mandatory. Why? Because complexity, look, this is the curve of complexity, increases a lot. A system, we need to make a distinction between complicated and complex. Complicated is sometimes when it's not very well done, and you have a dish of spaghetti, for instance, that is not very well thought for some time, the accumulation of things. And complex, that means that there are a lot of interconnections among agents and systems. And this is necessary most of the time. So in fact, you need to better understand, you need to become familiar with this complexity. Something that I'd like to emphasize is that there is a real similarity between artificial intelligence and systems engineering to the point that we have groups working on AI for SC and SC for AI right now, where the concept of agent in multi-agent systems, for instance, is very similar to the concept of system in systems of systems in systems engineering. So in other words, I mean, we have a lot of exchanges between these communities, as well as with the human factors and ergonomics, of course. So the definition I like to take is human systems integration is human-centered design associated with systems engineering. So traditionally, engineering is technology-centered. And automation came naturally, in fact, to automate some functions, you know, that were difficult to be executed by people. And then we mixed automation and procedure following in this approach. But that led to structural and functional rigidity in both in design and operations. And the consequence is that people adapted to the system or needed to adapt to systems. Despite the fact that sometimes we hear that we design a user interface to adapt the machine to the user, but in fact, we designed the user interface. And this is a polemic, probably, statement. I'm going to have questions on this, but you adapt the people to the machine. So instead, today, we have this coming and already installed, actually, digital engineering with virtual prototypes and all kind of things that enables you to do the overall system as a piece of software and hardware, but mostly software. And you can test the activity, as I said before. So you can start to do human systems integration. You can do the human-centered design, and you could associate that with systems engineering. This is very important. This is very new. So we can talk about autonomy in a sense. And in fact, I'm more interested in human autonomy than machine autonomy at this point, because what do you do when you need to deal with the unexpected? You need to solve problems. Well, probably first, you need to state the problem, and that's probably the most difficult. So you need to use human factors, modeling and human-in-the-loop simulation. This is what we do right now. And as a matter of fact, data science and artificial intelligence could be useful here. Instead of rigidity, I like to emphasize flexibility, structural and functional flexibility in both design and operations. And then what you need is creativity methods and tools, complexity analysis, agility development, tangibility analysis and solutions, and deal with maturity. And here, maturity is not only the technological readiness level, it's also the human readiness level and the organizational readiness level that you need to think about. So in fact, in this framework, we could think in terms of co-adaptation of systems and people, where system include people. So it's a recursive statement here. So this is what HSI is about. So summarizing, problem solving should be emphasized in both engineering design, and operations. My recent book I think is out for the last 2 weeks now. Emphasize design for flexibility. But the questions that we need to answer is what kind of support, what kind of technology could be useful for flexibility? What kind of organization? What kind of competence? Let's take an example. If you write a text, for instance, okay, you make a mistake and then you want to correct that. If you don't have the undo function, you're pretty stuck. This is pretty rigid. If you have the undo, this is becoming flexible. So undo is a flex tech. Another example is this, you know what this is? This is coming from a movie, the Apollo 13 movie, where the flight director asked a group of engineers to find a procedure to set up a CO2 remover in the capsule of Apollo 13. This was collaborative problem solving. Very, very nice setup. We could, you know, Apollo 13 mission was called and the accident was called the successful accident because they managed to solve the problem all together, the ground people and the astronauts. The ground people sent the procedures to the astronaut who executed the procedure, and they managed to come back safe to the Earth. Another example, this is in design. I had the chance to participate in the design of the Lunar Electric Rover. It's called now Space Exploration Vehicle. And we started with this kind of thing. You know, we had brainstormings for creativity, but also experience for very, very knowledgeable experts and you know, geologists and computer scientists, aerospace engineers. And then we had two artists who were making cartoons, and we were all over the room. We were putting post-its, you know, and around this storytelling thing. So we incrementally built, you know, this lunar rover. So creativity and experience should be associated, and sometimes they could be contradictory. You know, experience is very conservative most of the time, and creativity is, of course, the opposite. So, but you need to associate that in both operations and design in this case. So flex tech, technology, organization, and people. It's human-centered design and operations. Flex tech technology, problem-solving support. The undo, I summarize. Problem-solving team, the Apollo 13 example. Problem-solving competence, creativity, and experience. These are three examples. Now, integration. Remind you, the title of my talk was Human Systems Integration. The need for a systemic ontology. We cannot do it, you know, it's like if you have an orchestra, the orchestra needs a music theory. First, what is a system? What I learned at school is that a system is something, when you isolate the system, when you provide an input, the system provides an output. This is a logical, it's like y is equal to f of x in mathematics, for instance. But let's put it more theologically, saying a system, first, a system could be a human or a machine. It's very difficult to accept that the human is a system, but listen to the doctors, the medical doctors. They talk about the cardiovascular system, the cerebral system, the cognitive system. So we are a system of systems, human system or natural system. This is a representation. A system is a representation. The same for a machine. You know, the carburetor is a system inside an engine of a car. And then a human may include a system, like for instance, a human may include a pacemaker, you know, and a machine can include a human, like a car includes people. And then a system is characterized by a function and a structure, or functions and structures. That could be cognitive and or physical. You know, if you look at the brain, I mean, you could think, but it's physical in the sense that you have neurons and things, something physical. Same thing for the structure. Now, I like to expand this initial definition of system, isolated system, from providing outputs from inputs to the system of systems representation. A system includes several other systems interacting among each other. And a system is part of a bigger system. So in fact, this is a recursive definition. Now, I said a system includes, is defined by a structure and a function. And a system of systems is defined by a structure of structures and functions of functions. The difficult thing is to superimpose the functions on top of the structures. That could be done a priori when you design something. But when you put the system of system at work, then you have these yellow functions emerging. We call that emergent functions, and that you need to include in the design afterwards. So that means that design is necessarily iterative. And then you may forget the structure. And then, oh, oops, I forgot to put that. And then you need to incorporate this structure. So this is the reason why we need to have a representation that is flexible enough to make these incremental modifications. We have criteria to say, well, I should consider this function or this structure because it's important. And this criteria could be, I listed a few there. Shared situation awareness, that's something very important. Speed and precision of the activity, resilience, and trust and collaboration. We are working pretty much on this kind of thing right now. So this is being done at the moment. We have a project with my students on the future combat air system in Europe, where all this is trying to be modeled. I talked about situation awareness. I recently wrote a paper on this, expanding the Mika Hensley's model, where I put, a few more things. In fact, I tried to put the concept of real situation that you never really know, because it's so complex that it's difficult. But what you have is the available situation, because you have sensors that make these parameters or states available. Then you have the expected situation that actually drives the internal sensors of people and transform that into the perceived situation. So the perceived situation is probably smaller than the available situation, that is smaller than the real situation. And then after that, you need to interpret, you need to understand what is going on. So not because you perceive it that you understand it. Then you call the meaningful situation. And then in order to be able to do something with this information or situation, then you need to project yourself. This is Mika Hensley, so again, model. You have the projected situation, okay? To this, we need to add two other situations that are called the desired situation. It's different from the expected. And then the background situation, the experience and expertise. Something that it's deep knowledge. Then what about human-centered AI-supported machines? We need to work on both expert and public trust. This is different. People who are very acquainted with the system are very different, react very differently from the people who are occasional or really novice. AI certification. Can we certify AI machines? We are working. I mean, I've been interested for quite a while on this single pilot operations, and in fact, it's really interesting to consider this. I mean, I've been working on commercial aircraft certification for a long time, and here we deal with something that is very extreme. As a matter of fact, we will probably need to certify a drone. Ethical dimension. What about transparency, non-discrimination, fairness? All these kind of things should be considered. Safety. Do we have the right standards for this, for these AI-supported machines? Protocols and methods. This is what should be developed. I already talked about that. The technological readiness level. This is what we do today for maturity. But we need to emphasize human readiness level and organizational readiness level. I have a paper coming that I call social ergonomics that emphasize this ORL. New assistance systems should provide more flexibility. And another question that is very important: what should be maintained from the past as a skill for people? What should be acquired, and what is critical? All these kind of things should be emphasized. Then, I presented this systemic approach of human and machines together, but these systems of systems need to interact among each other. I propose 3 models of interaction. The first one is called supervision. You have a system that supervises the other ones, like a general in the army, and several layers, of course, of supervision. The second is the mediation. You have 2 countries, for instance, on the left and the right, and they want to interact with each other, and they have diplomats in a mediation space that enables them to understand each other and to interact. This is exactly the same thing for the desktop, for instance, on computers. That enables you to interact with the inside of the machine. You don't understand what is going on in the machine, but you have the user interface that is a mediating representation. And the third model is the cooperation. The cooperation requires each agent or system to have a model of the environment, of the organization around it or him or her. This cooperation model, systemic interaction model, is very valid for humans, but for machines, we are struggling right now. I mean, people in AI try to show that with machine learning, we can learn the model of the environment and things. Google, for instance, for quite a while now, spies what you're doing on interacting with in your Google searches, and then as a model of who you are, so prevents you some advertisements or things like this. But I think we are far from what humans are capable of doing. So where is the authority there? This is one of the very important questions. And also the autonomy. There is an axis here. From supervision to cooperation, there is an evolution of autonomy here. And then also of knowledge. This is okay. And then on these 2 axes, knowledge and autonomy, I think you can locate, pretty much these 3 models. Of course, if the cooperation model doesn't work at some point, then you can downgrade and go back to the supervision. Integration. Integration emphasizes the shift from purpose to means. Let me show you what I mean here. During the 20th century, we built a lot of engineering systems. Nuclear power plants, for instance. So we engineered this means to make energy power, nuclear power. We started from a means. And then we realized that there were people actually who were there to handle and to monitor and to control this means. And then guess what? We put a user interface in between, I mean, the control rooms here in this case. And we worked on ergonomics and automation. And so the thing is here, we if I try to make something more theoretical, we build a physical environment, you know, with real human agents and real machine agents, and then a control and management space, and then human in the loop protocols. I call that tangible human-centered engineering. This is inside-out approach, from inside the technology, outside to the people. And that's involved engineering, ergonomics, human-computer interaction, and automation. And this is actually the opposite of what I said before that we should be doing, is we went from means to purposes. In other words, we build the thing and we try to better understand how to use it. Now, 21st century, I'd like to show you that we can invert this approach. Today, we start any engineering design project with a PowerPoint slide deck. We show at work, we show the purpose, we show, you know, we build a model, we build a simulation, we build a video game, and we can try this virtual thing before anything is built. Look at the aircraft that have been built for the last 15, 20 years. So it's outside in, from the purpose to the means, in fact. The problem is tangibilization, as I said before. We need to make sure that what I've done in the virtual world could be tangible. And then the idea is to tangibilize incrementally what they've been doing. And this is actually the challenge of the 21st century. This is the challenge of HSI, going from purpose to means. I use the term tangibility. What is it? Tangibility could be understood in two ways. First, you know, I grasp this pen here. This is physically tangible. Now, I try to convince you. You're not so convinced. I hope not. I mean, but you're not so convinced. And you said to me, what you're talking about is not tangible. It means that I cannot grasp not a physical object. I cannot grasp the concept, the abstraction that you're developing. So the issue here is to mix this tangible, this physical and figurative tangibility together. And this is becoming more and more important in our digital society. How do we grasp virtual things, both physically and cognitively? Situation awareness is at the center of Industry 4.0, in fact. Fortunately, we have this virtual prototyping, modeling and simulation, human-in-the-loop simulation that enables human-centered design, that enables activity-based development, in fact. Going from purpose to means, leading to the fact that the user interface today is a component of the overall system from the beginning, and not something that you put on top of a system in the end. From purpose to means requires methods. I'm proposing here a method. I know that the time is running and I have no time to really develop this approach, where we mix procedural scenarios, scenario-based design, storytelling, you know, with declarative scenarios, configuration design. And this is what we want to do, the purpose, the analysis of the existing so far, anticipating possible future. This is where expertise and experience and creativity should be put together. Making a multi-agent ontology here at this point, and becoming more generic incrementally. We developed this method that we call PRODEC, procedural and declarative design. We are using this in a project on offshore oil and gas multi-agent telerobotic system, where we started in the virtual world, and incrementally we are adding robots that will be installed on drilling platforms for real in the end. Concluding, we need to be aware of the various possible contexts when you design something. It's impossible to have everything, but try to have as many insights and real representation of possible context as you can. That means that you need to develop scenarios coming from storytelling, coming from try and errors, simulate them with human in the loop simulation, convince your hierarchy that even if it's a little bit expensive, they will actually gain a lot in the end, and elicit emerging cognitive functions. This is crucial for maturity. Scenario-based design is really important, and especially to build incrementally with what I said before, solid conceptual models. I like to emphasize something I've done for quite a while now, especially in my 2013 book. I developed the orchestra model, where, you know, to make a symphony really well, you need a music theory. That means that you need a common framework, interaction models, and the right definitions of the systems, what systems means, both humans and machines. You need composers, means scores that are contracts, in fact, among these systems. And then you need the coordination of this. You know, a composer who makes a symphony coordinates the various scores between the percussionist and the violinist in order to make things right. And then at performance time, you need conductors. This is dynamic reallocation all the time. And then musicians. That means that you need competence, engagement, and cooperation with the other musicians. And then the audience. This is the, you know, the when we talk about end user centered design or something like that. I mean, the people who, the customers, if you want, for the symphony. I mean, the people who listen to the symphony. But here is so the idea here is constant communication and education. I realized this very, very well at NASA. What do we say to the public that we do in space? The orchestra model. A few takeaways. We live in a digital world. I'm sure that nobody will contradict that. And tangibility is a crucial temporary issue, the way I define it. Single agent ergonomics is not enough. People in front of a machine, you know, facing a machine. Then, you know, we need really to go to social ergonomics. I know that in the room, there are many people working on this for quite a while, but I want to really insist on this. This is crucial today. Human-machine teaming. What are the new human roles? Because we deal now with systems that are much smarter than before. Not necessarily the intelligence that we could understand all the time. And this is why we need to better become familiar, actually, with these human roles and human-machine teaming. Rigid automation is what we know today. Flexible autonomy is what we need to make. How do we deal with the unexpected? Well, we need to develop more problem-solving support, technological, organizational, and new competencies. From means to purpose, this is what we have done for a long time. People adapt to machines, of course, using user interfaces. But what we should target is from purpose to means. Machine adapts. They may not adapt in a machine learning way immediately. That could have several long cycles, but we need to better understand the mechanism behind this. Collaborative work, which is, I think, the key issue here, dealing with social ergonomics, new human roles, flexible autonomy and everything, and problem solving, etc., requires education. We should not limit education to the late years of university. We should start much earlier, probably at school. Openness, empathy, and enthusiasm. I am enthusiastic with this. I am very positive about the future. I think we should go in this direction. If you want to read more, this is more than 200 pages that you can read on this topic. This is the last one I already talked about, design for flexibility. And I like to advertise this conference organized by INCOSI in cooperation with the International Ergonomics Association, the Association for Computing Machinery, and the Air and Space Academy. Will be held in November this year in San Diego, hopefully, otherwise it's going to be virtual. We will know that in September. So look at the website and you will have the information. Thank you very much. That was a pleasure to give this keynote, and thank you for the organizer to invite me.